Hi, everyone. We are back for more pre-calculus fun. And, can you tell me what movie this background is from? Let's see. Okay, so we are starting a new chapter now. Where's my thing? There it is. And it is um, chapter 10.1. And it is about, oops, let me move that thing down. It is about derivatives, introduction to derivatives. Derivatives, super important. You're going to take calculus, you're going to need to know derivatives. So this is probably the most important. Chapter 10 is probably the most important thing for all of you. So I would pay careful attention and enjoy the homework and definitely do it. Because you're going to have to do this stuff again. I know this because I taught calculus last semester, so I know it's going to be there. So let's start out with some definitional things here. First of all, if I want to calculate my average velocity, or I could say, you could say speed if you want, it would work. Let's see, units for speed are miles per hour. So that would be distance over time equals velocity. And the book is going to use not distance, but displacement over time equals velocity. Displacement is the distance from where you are compared to where you started. So it's a difference. So it's like D2 minus D1, right? Where you are after 2 seconds minus where you started from, whatever that is. Okay, that's going to be your displacement. And so we can write an equation. I'm going to write this as the velocity as change in displacement over change in time. Delta means final minus initial. And this is the Greek letter delta. Okay. And so we'll write that as final minus initial. So we have an equation here for the velocity. And I could plot, let's say your displacement versus time. Let's say you start here and you walk over to here and you travel after 1, 2, 3 seconds, you go 1, 2, 3, 4, 5 meters. So you're at this position, 3, 5 on our displacement versus time graph. And they ask, how fast did you go? So your speed, your velocity, would be the change in displacement over change in time. So that would be, let's see, change would be final minus initial. So that would be 5 minus 0 over time, 3 minus 0. It would just be 5/3 meters per second. Okay, so that would be our distance. And that looks surprisingly like the slope equation. And you know why? Because it is. On a displacement versus time graph, slope equals the velocity. And so what we just found was the slope. The slope of this line tells us the velocity. Well, that is super interesting. I'm sure you're all extremely excited about that. But let's get rid of some of this goop. Okay, so you're thinking, yeah, Mark, but when I'm walking to go get some food, I don't walk, I run. I start out slow, but then I speed up and I get up to here at 3.5. That's how I roll. You're walking along because you're old. Yeah, true enough. But you're going to run. So you're going to start out slow, but you're going to speed up and speed up and speed up. And let's say you go through the point at 1 second. You make it 1, 2. You make it 2. We got a point here. 1, 2. And so I could still calculate my average slope, right? And it's going to be the slope of that line if I just use 3 and 5 and 0, 0 to calculate the slope of that line. But I wouldn't say this dotted line represents the curve very well at all, because look at all the space in here. All that open space is error. The slope of this line does not describe this curve at all. But let's make a better one. What if I made this line? Well, that looks better, right? I mean, look at, instead of that big space in there now, the space is less. So the line more closely hugs the curve. So this line is more accurate. So I could go and calculate the slope now of that line, and it would be, let's see, slope is y2 minus y1 over x2 minus x1, or it's change in displacement over change in time. So we'll plug it in. Final initial. So this would be 5 minus 2 over 3 minus 1. So this is going to give me 3 over 2 meters per second. Okay, that's a better representation of the graph. But let's say we got a point here that's at 2.5 comma 4. Well, if I try to draw the line there, let me get a line, got a line. Let me get a pretty color. We'll get some purple going on. So if I draw this line, well, look at how close that is. I can barely even see a space between the line and the curve. So if I go and I calculate that slope, turn that off. So that slope is going to be, let's see, y2 minus y1 over x2 minus x1, 3 minus 2.5. So that's 1 over 0.5, which equals 2 meters per second. This is way more accurate than what we did with this blue line or even our original calculation. This is a more accurate representation because the line hugs the curve closer. I mean, look, you can barely see any space in there. Look how close that is. So what I want you to realize is the 2 points we use to find the slope of a curve, the closer together they are, the better representation they are of the curve. Okay? So we want to get these things as close together as possible, the 2 points, so that when we calculate the slope, that slope more accurately represents the slope of the curve. Okay? And that's the story around derivatives, is we're going to do that. Okay, so let's say we have a function. S of t is t squared. And this is in feet. And time is in seconds. And I want to know, find the instantaneous velocity at t equals 3. Well, instantaneous is a new word. So far we've done, right, I had my curve and we did 2 points and we got the slope of the line between them, and the closer the points were together, the better the calculation was. But all we were doing was finding the slope between 2 points. We were finding the average velocity. And the way you find the average velocity is the slope between 2 points, y2 minus y1 over x2 minus x1. So that's what we just did on the previous page. But now I want the instantaneous. I want to know exactly what it is. I don't want an average that is close to the curve but there's still some space in there, so there's still some error. I want it to be exact. And that's what instantaneous means. It means exact. So how do we do that? Well, we have some ideas. I know you don't think you have some ideas, but you do. So if I want to find the velocity, I'm going to do change in displacement over change in time, which means I'm going to pick 2 points. And so here's my curve. Whoops, that's a bad curve. Here's my curve. And here's t equals 3 seconds. And this is S of t, and this is t. 3 seconds. Okay? Well, I'm going to pick 2 points and find the slope. Should I pick 0, 0 over here? Is that a good choice? No, because look how far away it is. That's never going to be a good representation of the curve. When I draw that line, there's going to be a huge amount of space in here, which tells me there's a huge amount of error between those two. I want to choose something closer. Why don't I pick t equals 3.1 seconds? How's that sound? Ooh, that sounds exciting. Pen. So I'm going to pick 3.1 seconds. Okay, now we're talking. So I'm going to put in 3.1 for t, so that'll be up here, 3.1 squared, because I'm using a t of 3.1. So let me write the coordinates here. So this is going to be x is 3, y is going to be 3 squared. And then for this one, it's going to be 3.1. Oops, let me write it over here because I won't have room. Oops, sorry. This point is going to be 3.1 comma 3.1 squared, because I'm plugging 3.1 in for t, and t squared is 3.1 squared. Okay, let's figure this out. So here's my point 2, here's my point 1. y2 minus y1 over x2 minus x1. So what's this going to give me? Let's see, I'm going to do this, and that comes out to be 0.3025, obviously, over, oops, I did that wrong. Sorry. Let me calculate it again. There we go. 0.61 over 0.1, which is 6.1 feet per second, because I said we were in units of feet and seconds. Okay, there we go. Is that exact? No, it's not exact, because these 2 points are separated by a time of 0.1 seconds. Can we get closer? Yeah, we can get closer. We could try, let's try 3 and 3 squared, and we'll try 3.05 and 3.05 squared. So we'll try, instead of using 3.1 seconds, we'll use 3.05 seconds. Okay, now we're cooking with gas. This is going to be awesome. So it'll be y2 minus y1 over, I'm looking over here, this is 0.2, this is 0.1. These are my 2 points on the curve. I can't really fit them because it's going to be right in here, right? It's getting kind of crowded. Okay, 3.05 minus 3. Okay, let's do that. Let me get my calculator out. Beep, boop, boop, boop. That comes out to be 0.3025 over 0.05. And that comes out to be 6.05 feet per second. Well, this must be more accurate because the space between these 2 points is less. So, but they're not exact. They're not the same. So what do I want these 2 numbers to be? What do I want to use here so that I can get exact? How much space should there be between T2 and T1? Yeah, the space between them should be 0. I want to use 1 point. I don't want to use 2 points that are separated. I want those 2 points to be right on top of each other and find the slope with those 2 points. And we can do that with a limit. Limit as t approaches 3. So instead of using a point, I'm just going to use the variable t, because that's our function, right? T squared. So I'm going to use t squared minus 3 squared over t minus 3. This is the x coordinate for that point. This is the x coordinate for that point. And so this is, oops, I got to do my little limit thing. Limit as t approaches 3. So this would be t squared minus 9 over t minus 3. Oh, and you're thinking, wait a minute. We can factor that numerator, Mark. Don't be an idiot. Okay, I won't be an idiot. So this will be t plus 3 times t minus 3. Those are t's. All over t minus 3. And the t minus 3's will cancel. Now I can plug my limit into the function because I'm not going to get a 0 down here. So I'll get 3 plus 3. The instantaneous velocity is 6. That is the exact number for the slope right here at 3 for this function t squared, 6. That is the exact instantaneous velocity. Okay? So this is how we find the instantaneous velocity. And you're thinking, holy crap, that is a bunch of stuff. And you're right. So we're going to do some more. But I want you to think about some things first before we get to some more. And that is, if I have a curve, oops, with a flat spot, I don't want a flat spot. There we go. And I want to know what's the instantaneous slope right there. The instantaneous slope, the instantaneous speed in the case of a displacement versus time graph. It may not be displacement versus time. It may just be f of x and x, whatever. The instantaneous slope is the line drawn between this point and itself. And the way we represent that, let me see if I can draw it. Nah, I missed. Over here a little bit. Oh, there we go. That looks good. Still missed a little, but that looks good. So that line right there is called the tangent line. And the tangent line touches the curve in one place. Okay? And the slope of the tangent line is the same as the instantaneous, I always have trouble spelling that word. Oh, and I did it wrong, didn't I? Isostaneous. There you go. I missed an N. There we go. Instantaneous slope. So the slope of the tangent line is the same as the instantaneous slope of the curve. So whatever the slope of this line is, it's the same as the slope of the curve. Man, if I knew 2 points, I'd be in business because I could just find the slope of that tangent line and that'd be the slope of the curve. And you know what? You never have this other point. You'll usually have this point because a problem will say, calculate the instantaneous slope at the point 3, 5 or something. It'll give you the coordinates, it'll give you the x and y, but that's all you're going to get. And you need to figure out this instantaneous slope. Okay? And that's what we're trying to do. And so if we have, so if I do, and we'll do this one again, it's f of S of t is equal to t squared, and we want to know instantaneous slope at the point 1, 1. Okay? So I'm going to take the limit. First of all, this is x and this is y, right? Take the limit as t approaches 1 of s of t minus s of 1 over t minus 1. So notice this one and this one and that one and that one are all linked together. If we were doing it at the point 3, then these would all be 3s. If it was at the point 7, these would all be 7s. But you see the challenge with this is, if I go back to blue and I write my thing again, limit as t approaches 1 of s of t minus s of 1 over t minus 1. I can calculate what s of 1 is. I can plug it in, right? I can see what that is. But what happens when I plug t into the denominator here? I'm going to get t minus 1. And that makes us sad because we got a 0 in the denominator, which means we can no longer play with our function. We have to send it off into the cornfield. If you ever saw that Twilight Zone, great Twilight Zone. Send it to the cornfield. Okay, so if I'm going to do this, let's do it. Limit as t goes to 1 of s of t is t squared minus s of 1, so I put 1 in there, 1 squared is 1, over t minus 1. And I'm going to write this, don't forget our little limit business, as t plus 1, t minus 1 over t minus 1. And these will cancel. We'll end up with t plus 1. Now I can plug the limit in. 1 plus 1. I put 1 into here. Is 2. This is the limit as t approaches 1 for this thing. This is the instantaneous slope at the point 1, 1. This is our slope. This is our slope of the curve right here at 1. Okay? That tangent line has this slope. And this is how we do it. And you're thinking, well, what if this thing didn't factor and this thing didn't cancel? Well, guess what? They have to cancel or you can't do these. So that's always going to happen. But there's ways around it. We can deal with other things here. So let's give a definitional formula. Slope of tangent line. Okay, slope of the tangent line equals the limit as your variable approaches some number of f of x minus f of a over x minus a. This is how we're going to find the instantaneous slope, or the slope of the tangent line to a curve at the point A. So this point is going to be the x coordinate, and the y coordinate is going to be f of a. Hey, look at that. That's right there. Imagine that. Okay, so here's going to be the thing you're going to do. And you're going to leave f of x a function. These are going to be variables. These are going to be numbers. You'll plug in the variable, the function, you'll plug in the number, x minus a number, and then you're going to do some algebra to get something to cancel out that denominator. Because when you put a in for x, you can't have this down here because it'll become 0 and the whole thing will go boom, and you won't be able to do anything. But now there's another way to write it that's much more convenient. And I'm going to make a little substitution. Let x equals a plus h. Okay? And you're probably asking, why do we do that? Well, I do that because I know the answer, and I know this makes it a little easier. And just for fun, if I solve for A here, I'm going to move the H over to the other side, X minus H equals A, right? Okay, so if I plug that into the denominator, well, let's see. So now let's make this substitution. So here's my thing. Limit as X approaches A. Well, no, I'm sorry. That's not right. So now when we make this substitution, we're going to end up with this. The limit as H approaches 0. H is the distance between these 2 points. So this would be my 3 and my 3.1 on the last example. Well, this would have to be the 0.1. So this is the distance between the two. And we want to shrink H. We want to get that distance between the 2 points to be as small as possible. So let's see. I'm going to write this as f of x plus h minus f of x over h. And this is the way we're going to use this function. And this function is the slope of the tangent line. It's also the derivative, which we write as f prime of x. This is the derivative of f of x. What is the derivative of the f of x? Derivative of f of x is the slope of the tangent line. So this will give us a function that we could plug any value of x in, and it's going to spit out the slope of the tangent line. And this is the real meat of calculus right here. And this is the important thing we're going to use. And in homework problems, last year I assigned homework problems number 23 to 31, and you used this function for them. I don't know if we'll do those homeworks this year. I haven't really chosen those yet, but we'll see. I promise you'll have fun homework. It'll probably be the same. Okay, so let's say we have the function. This is example 4 in your book. So we have the function f of x equals 2x squared minus 3. And I want to know what's the derivative, what's f prime evaluated at 4. So this means what's the instantaneous slope at x equals 4. This means what's the slope of the tangent line at x equals 4. This means what's the derivative evaluated at x equals 4. All three of these statements mean the same thing. Derivative, slope of the tangent line, instantaneous slope, same, okay? That's what we're looking for. So I'm going to use my function. So f prime of 4, let's use the thing I wrote. So that's going to be the limit as h approaches 0 of f of x plus h, so 4 plus h minus f of x over h. Oh, that's it. Oh, isn't that fun? Okay, so let's go ahead and plug it in. First, let's plug in 4 plus h in for x. This is like with those composite functions we did. Oh, that's why we did those. Limit as h approaches 0 of, this would be 2 times 4 plus h squared minus 3. That's this thing. Minus f of 4. What would f of 4 be? So that would be 2 times 4 squared minus 3. That'd be 2 times 16 minus 3, 32 minus 3, 29. Okay, 29. All over h. Now we got to FOIL this thing. 4 plus h squared will be 4 plus h times 4 plus h. Oops. So it'd be first 2, outside 2, inside 2, last 2. So I'll write it in h order. H squared plus 8h plus 16. Okay, so I can rewrite this. Limit as h approaches 0 of, oh, and I got to do it times 2. Woo, almost forgot. So this will be a 2, and this will be a 16, and this will be a 32, right? 2h squared. Well, let me just write it out. Forget that. So 2 times h squared plus 8h plus 16. This was what we originally multiplied out. Minus 3 minus 29, that'd be minus 32, okay, over h. H goes to 0, so this is 2h squared plus 8h plus 32, and then minus 32. And notice these cancel. Those better cancel. If they don't cancel, then you did something wrong, because I need to be able to factor an h out of the top and the bottom to make this one go away. And I can't do that if these numbers are still there. So if these don't cancel out, you did something wrong over here, or you did something wrong over here, or you got up in the morning and you should have stayed in bed. One or the other. So those have to cancel. So we get the limit as h goes to 0. I can factor an h out of the top, and I'll get 2h plus 8, right? All over h. And these are going to cancel. Now, I've gotten rid of my troublesome denominator. I can plug h equal to 0 into my function. So I'll plug h equal to 0. 2 times 0 is 0, plus 8 is 8. Oh, here it is. This is the slope. This is the instantaneous slope of this function at x equals 4. This is the slope of the tangent line for this function at x equals 4. This is the derivative evaluated at x equals 4. So I could say f prime of 4 equals 8. And that's it. This is the process. And the place where people get messed up is, first of all, you got to write this down correctly. If you don't write this down correctly, you're done. So you got to do that. And this is easy. You're going to have some examples written out on a cheat sheet whenever you take a test or a quiz, obviously. I'd rather you didn't. I'd rather you remember it, but come on, it's online. You're going to do that. And then you got to multiply this thing out right here, right? You got to do the whatever the function says. You got to FOIL that thing out correctly, and you got to get the right thing. Then you plug what you multiplied out back into here, and then you try to simplify the numerator and hope these two things, these constants, cancel, because you want an h in every term in the numerator so you can factor it out so that it will cancel out with the bottom. If you don't get an h here that you can pull out to cancel the bottom, then you did something wrong and you're going to get the wrong answer. Okay? You have to do that. Okay, let's see if we have another example. Hey, look at that, we do. Okay, this is example 5 in your book. So we have f of x equals x squared. And we just want to find f prime of x. I'm not going to give you a number. I want a function so that I can plug a number in and get my derivative. Okay, so let's do this. Limit as h approaches 0 of f of x plus h. Let me write that a little neater so it doesn't look like a plus sign. X plus h minus f of x all over h. This is the definition of the derivative. Now we plug into here. So this is going to be limit as h approaches 0. Notice we can't plug h in because we got h down here, and we'll get a 0 if we plug a 0 in. That's bad. So we got to keep going. So f of x plus h is going to be x plus h squared because I'm plugging f of x into, or x plus h into my function f of x. So I put x plus h into x, and oh, it says square it, so okay, I'll square it. Minus f of x, and f of x is just x squared all over h. Okay, what do we do next? We FOIL. X plus h, x plus h. So first two, outside two, inside two. Oops, wrote a y. Last two. So x squared plus 2hx plus h squared. Okay, so let's plug it in. So limit as h goes to 0 of that big nasty thing, x squared plus 2hx plus h squared minus, minus x squared. Okay, that seems bad. Oh, well, let's see, over h. And let's see, what can we cancel? These will cancel. This one will cancel that one. And that's a great thing, because if these x squares cancel, then I'm left with things that all of them have an h. And that makes me really happy. So I'm going to write this as limit as h goes to 0 of 2hx plus h squared over h, which I'm going to write as, I'm going to factor out an h. So I'll be left with 2x plus h over h. Hey, look at that. They cancel. I did it right. Yay. Okay, now I can plug in h into my function because I don't have a 0 in the denominator. So I put h in here. That's going to be 0, and I'm going to get 2x. So the derivative of f is 2x. This means for my function f of x, if I want to know the slope of the tangent line at any point at x equals 4, well, I can plug it right into here. 2 times 4 is 8. The derivative at 4, oops, sorry. I plug 4 into here, 2 times 4 is 8. So this is the derivative function for f of x equals x squared. This function tells me the slope of the tangent line at any point x. This is very powerful. So I could have a really complicated function. Of course, this would be harder. But if I had a really complicated function, like that, if I had something like this, it would tell me the slope anywhere on this function. And that would be a great thing to have if I'm using this to predict forecasting performance of a vaccine, for COVID, right? Knowing the slopes helps you predict a little bit ahead, and that's really valuable. So this is how we do finding the derivative of a function. And this equation we started with is super important. Muy importante. Muy. Okay? So there's tons of problems of homework that you're going to need to do. You're going to need to do this multiple times until you get the pattern down. Don't think that you're just going to do this once and you get the right answer and awesome, you're good to go. Because when you get to a test and you got to do this, and if you don't remember the pattern, you're going to be stuck. Okay? And if you have to go hunting for it in your book or somewhere else, you're going to run out of time and you're not going to finish the test. So it's easier to do the homework and ask questions and make sure you learn the patterns, because this is all about patterns and that's all it's about. Okay? So please come to the office hours and I'll do some more examples and you can see how to do some of that homework, and you'll be successful if you practice this. Thanks for watching. We'll see you next time. One more chapter left. Yay. Bye.